action applied on the surface, right? I use superposition. So finally, I give you a formula, right? Formula, I leave the formula in terms of the integration, right? So you need to perform the integration whenever I gave you the loading condition. For example, this is the assignment number 3, right? So I ask you to use the formula that I derived, okay, and you need to consider all loading conditions like this, and then you use the formula that I gave you to compute displacement and suppress at any location. So basically, this assignment, I didn't ask you to solve the problem again. Basically, I asked you to use the formula that I derived and try to get the elastic field, like displacement, suppress, okay, and then I asked you to plot some results, right? Okay, along some along some direction. Okay. So in the assignment, you are allowed to use any tool. You can use any integrator that available. Okay, I don't suggest to do it by hand because performing the integration by hand will take some time. So you could this day there are many available tools that you can use to solve this problem, to solve it, to get the integration done. Okay. Today I will look at the same problem again, but I will solve the problem by different technique. Okay. The technique that I will show you here is based on Fourier transform. I think that you should be familiar with this type integral transform, right? Fourier transform can be applied to solve several classes of mathematical problems. Okay. For example, you can use to solve partial differential equations, right? Or ordinary differential equations. You used to apply that kind of technique before when you learn ODE, right? There are 2 types of the transform that you may be familiar with. The first one we call Laplace transform, right? And the other one is the Fourier transform. So here I will try to use Fourier transform to solve this problem. The reason that I use Fourier transform because the domain that we consider here, one direction. In one direction, the coordinate range from minus infinity to infinity, right? So if you think about the half plane that you have, okay, x1 range from minus infinity to infinity, right? In that case, it matches perfectly well with the Fourier integral, if you remember, right? If you try to transform a function in one direction, so you take the integration from minus infinity to infinity, right? So that works perfectly with the problem of interest. Okay, so if you are not familiar with this kind of technique, I suggest you to get some material from the website. Okay, do the search, and you can get the basic information of this kind of technique or this kind of transform, and then once you get the basic background in this kind of technique, now you can apply that to solve the problem. It's not complicated. Okay, the idea is very simple. Okay. So first, if you plan to use this kind of technique to solve problem, you need to list the key governing equation. Here I will try to formulate the problem in terms of the displacement, because for 2D problem, if you choose the displacement as the key unknown, you need to solve only 2 equations. Okay? So if you go back to different types of formulation that we have in the first lecture, okay, the number of unknowns, the number of key unknowns that we have to deal with depends on the choice of the unknown that you pick at the beginning, right? So if you pick all the field quantity as the key unknown, we have to solve many equations simultaneously. But here I will focus on the displacement formulation. So I will pick the displacement U1 and U2 as the key unknowns. I will work out the problem in X1 and X2 system here. Okay? So I go back to the formulation in terms of the displacement. If you remember, here is a set of two equations for 2D problem. So I express equilibrium equation in terms of displacement, or we call Navier equations. So this is the Navier type equations for 2D problem. For homogeneous material and isotropic materials. Okay, we have two material constant, and mu and kappa here are constant because I look at the homogeneous case. So mu and kappa are not a function of x, and we deal with only the isotropic material because we have the two constants. So if you can solve these two equations, get U1 and U2 done, right? So this is the way that I will consider using. I will use the Fourier transform to solve these two equations. Okay. So we have two cases, right? The kappa that appear in these two equations represent two cases, right? So for plane strain and plane stress problem, kappa are different. Okay, depending on Poisson ratio that you have for that problem. Okay, so I look at the domain of interest for half plane problem. This is the domain of interest, right? So we have x1 and x2. If I pick the coordinate system like this is your x2 and that's x1. So you can see that the half plane here occupy a region for x1 from minus infinity to infinity, right? But x2 range from 0 to infinity. So I will take the Fourier transform alter in these two equations with respect to x1 coordinate. Okay, I take the Fourier transform of these two equations. Okay. But if you cannot remember the definition of the Fourier transform, let me introduce the basic definition of the Fourier transform here. So let f here is a function of two variables. F is a function of x1 and x2. I define the Fourier transform of that function like this. Okay, I convert. You can say that if you have a function of x1 and x2, once you're done with the transform, you convert the function to function of sine x2. So x1, the argument x1 is removed from the function by performing this integration, right? So e to the I sine x1 here is the kernel. So this is the kernel of the transform. Okay. So you can see that when you take this integration, x1 here disappears because x1 here is simply dummy of integration, right? So once you done with the integration, x1 disappears. So now you can say that okay, the transform here is just simply the process that you change from the function f from a function of x1 to a function of sine. And sine here is the transform line. Okay. Okay, I use the symbol f bar to represent the transform of a function f. Okay, and now f bar is a function of sine and x2. Okay. I that appear here is simply the imaginary unit. I is simply the square root of -1. You should be familiar with this I, right? Okay, you learned it before. Once I give you a function f, you can get f bar by simply performing this integration. What happens if I give you f bar? Can you get back f? I give you f bar. Let's say that again. Your friend take one function and perform the integration following this formula. So your friend will get f bar, And let's say that your friend give you this f bar, can you go back and get this f? So we have to do the inverse process here, right? So we can do the inverse Fourier transform. We can get back the function f if we know the f bar. So this formula will allow you to get a function f, the original function f, once you know the transform of that function. Okay, you just simply plug in f bar back into this formula. Okay, you get the transform like this. Okay, and also we will have some properties like the derivative of a function. So if you take the transform of the derivative of a function, you can simply take the transform of that function and multiply by this function. Okay, how can we prove this? You can go back and read some books or references talk about the property of the Fourier transform. So it's not very difficult to prove this. What I try to say here, you can see that the transform of the derivative of a function can be converted into the transform of a function itself. Okay, or you can say that the derivative here can be removed, right? Can be eliminated and replaced by the transform of the function itself. Okay, but you need to modify the transform of the function by this quantity. Okay, so this property is very useful because you can change some of the derivative that you have in this equation. You can eliminate some of the derivative based on this property. But make sure that the derivative that you look at here have to be the derivative with respect to x1. Okay, x1, you try to transform f with respect to x1, right? So here you can see that we define f a function of x1 and x2, right? So we transform function f with respect to the variable x1. Okay, and this property valid only when you take the transform of derivative of function with respect to x1, not x2. Okay. Based on this definition and also this property, now I can apply the Fourier transform to both equations they have there. So this is what I got. Okay, I apply Fourier transform to the equation. I will get something like this. So here I just take the transform to each term. This is simply constant, so I don't need to worry about them, right? Because they're just constant. So I take the transform of that term, that term, that term, that term, right? Okay, the transform of that term, you can use the property that I showed you before, right? Because this is the transform of second derivative of the function with respect to x1. But this one, you take second derivative with respect to x2. In this case, you cannot do that property because the transform is performed with respect to x1. Okay, so if you have second derivative like this, so now you can move the transform here to u1 directly. Okay, so this is what I got. Okay, I use this kind of property. Any derivative with respect to x1, I can replace it by this kind of property. So finally, I will get this equation. I'm not sure that's clear to you. For example, this one now is replaced by that one using this property, right? In this case, n is simply equal to 2, right? N is equal to 2. So now you get minus I sine square here, and you get u1 bar. You take the transform of that u1, right? So I use this property with n equal to that term, I will get this term, right? For the second term, because the transform here is with respect to x1, but the derivative here is less, derivative is with respect to x2. So now the transform here can be moved to u1 directly, right? Because x1 and x2 are independent. Okay, so now you can see that the second term becomes that one. And I change the partial derivative to the total derivative because whenever I transform u1 bar, now u1 bar is not a function of x1 anymore, right? So now I can change the derivative here to derivative with respect to x2. Okay? Because x1 disappears due to the transform. I apply this kind of idea to all the terms that I have. For example, that one, I get that term. And that one, there is one derivative with respect to x1. So I have minus I sine here, right? So it's enough with this term. I'm not sure that's clear to you. This one is a mixed derivative with respect to x1 and x2. I can use this property for the derivative with respect to x1 first, and then I can take the derivative of u2 bar with respect to x2 directly, right? Because x2 is independent of x1. Okay? So I follow this kind of procedure for all the terms that I have in both equations. So finally I get these two equations. Okay. Once you get these two equations, if you compare with the two equations that you have before you do the transformation, before you do the transformation, equations are in terms of the PDE, right? So you have partial differential equations, right? But now the final result that you got here, the two equations here are not PDE anymore because x1 disappeared due to the transformation, right? So x1 disappeared. So the two equations that you saw here are simply a function of x2, right? All the term and derivative as well. So I can say that these two equations are simply ODEs, right? They are ordinary differential equations. So solving ODE is simpler than solving PDE, right? And now you can apply what you learned before in your math class, right? Before you know how to solve ODE, right? At least for second order, you should be able to solve that, right? So I have two equations to ODE, right? I have two ODE with respect to the variable x2, okay? I can re-express the two equations here in a metric form like this, okay? In a vector and metric form for convenient for conciseness, okay? I group u1 bar and u2 bar as part of a vector u bar, okay? U bar here consists of two components, u1 bar and u2 bar, and the metric A. The metric A is simply 2 by 2 matrix like this, okay, with the entry like this. And the metric B is simply 2 by 2 matrix as well, and also for the metric C. Okay, so if you define the metric A, B, C, and vector U bar like this, you can express the two equations in this concise form. It's just for convenience. You will not have any problem if you keep expressing the equation like this, no problem. But I just feel that this form is more compact, right? So it's more concise. It's easier to understand, in my opinion. So I express them in terms of vector and matrix form like that. If you don't believe that the form here is correct, why don't you try to expand by replacing all this here, and then you expand it, you get back the two here. Okay. Now, how can I solve this ODE? A system of ODEs. We have two equations. How can we solve that? I will follow the standard procedure that you learned in math class before. Okay, so this is the procedure for solving the system of ODE. Before you solve this equation, I would like to make a note here. this ODE is linear, right? The form that you got here is linear. So all the terms that you have here that involve U bar, they are linear terms, right? They are linear terms. Okay, and the higher order of derivative is 2, right? So now I call this second order ODE, right? Second order, because you have the maximum order of derivative is 2, right? Here. So it's linear, second order. What else? The constant, the coefficient in front of the term, the second derivative, the first derivative, or even the function itself. The coefficient in front of them are constant. Okay, so we deal with a system of ODE, that linear, second order, and we have constant coefficients, right? And also, equation that we have here is homogeneous. Is that right? Because term on the right hand side is 0. Okay, so now we deal with linear second order homogeneous equation with constant coefficient. Okay, how can I solve this? How can I solve this type of equations? So this is the simplest equation that we can have for ODE, right? This is the simplest one. We have a standard cross here to get the solution, the general solution of this type of system. Okay, this is the way. Okay, first we will assume the form of the general solution. So this is the typical cross here. So I will assume the form like this. I assume that the solution of equation 1 take this particular form. U bar is simply e to the gamma x2 multiplied by the vector eta. The vector eta here is unknown a priori. Okay, I need to determine eta. And also gamma is unknown. I don't know the constant gamma here. Okay, gamma can be real number or it can be complex number. Okay, I don't know at this stage. Okay, I will determine gamma and also the vector eta. Okay, eta here is a vector with 2 components because U bar is a vector with 2 components, right? Okay. So how can we get gamma in the eta? We know that if the solution of U bar take this particular form, if we plug in U bar back into equation 1, it helps to satisfy. Okay, this helps to satisfy this equation, right? So if U bar equal to this is a solution of this equation, when you plug in this function back into this equation, you need to satisfy that equation at any point, right? So what I will do here, I will plug in U bar into this equation. What should we get here? So this is what you will get. It's quite simple, right? Because eta here is unknown constant, but it's not a function of x2, right? So you take second derivative of this one with respect to x2, you just simply take second derivative of the first term, right? So you know how to take derivative of exponential function, right? So this will end up with this term, right? So that is the first term, you will get this one, right? And the second term, you just simply take first derivative of this one, you get that. Okay, and the last one, you don't need to take derivatives. So what you will see here, you will see that you have the common factor, right? E to the e to the gamma x2, e to the gamma x2, e to the gamma x2 again for the third term. So now you can get things like this, and eta also is a common factor, right? So now you can explain the term on the left hand side like this, and the product here have to be equal to 0, right? Make sure that equation 1 is satisfied. So in this case, you know that this term cannot be 0. Is that right? The exponential function here. So now you require that term multiplied by a there have to be 0. Is that right? Okay. So I end up with this condition. Are you familiar with this type of equations? Equation number 3 here. If you take a look at the whole thing in the parentheses, what is the whole thing here? When you combine the first term, second term, and the third term, the whole thing here is simply a matrix, a 2 by 2 matrix that involves gamma. Because A, B, and C are 2 by 2 matrix, and gamma here is simply a constant, right? So when you combine the 3 matrices here, you will get a 2 by 2 matrix. And you have a 2 by 2 matrix multiplied by either equal to 0. What is the name of this type of equation? Eigenvalue problem, right? If you remember, I'm not sure. You should be familiar with this type of equation, right? So we have a matrix multiplied by a vector, and you get 0. Okay, that's what we call eigenvalue problem, right? So here we try to determine gamma and eta that satisfy this equation. Okay. I am not sure that you can remember this. Can you answer me? If I have a system of linear equation, I have a matrix A. I have an unknown x. X here is a vector. And on the right hand side, I get 0. How many rules that I will have for that system? Okay. Maybe you can look at the more general case. If on the right hand side is simply a vector p. Okay. This kind of system, if you talk about the root, there are 3 possibilities, right? The first one, this equation contains no root. Okay. Or this equation contains only one root, or contain an infinite number of roots. Only 3 possibilities that you can have for this kind of system, right? Is that right? Okay. Now, what happens when I change this to 0? How many possibilities that I will have here? Only 2, right? I am sure that I can eliminate the case that this contains no root, because you know that x equal to 0 is root for sure, right? So this equation cannot, this equation always have a solution. Is that right? Because you can try x equal to 0, right? 0 is always a solution of this linear equation. So this is homogeneous equation. So 0 is always a root of this equation. Now, we have 2 possibilities. The first one, 0 is a single root. 0 is the unique root of this one. Or the second case, you have other roots, and in that case, you have infinite number of roots besides 0. You have something else. Okay. But if you look at the problem that you try to solve here, are you interested in the case that this one contains only one root? Okay, if you say that okay, if this one have a single root, that implies that a has to be 0. Because 0 is a solution, right? So then if you say if you require that this one have a single root, now you have a equal to 0 as a root. And then what happens if a equal to 0? You buy 0. So that is the trivial root. You don't want to get 0 root in your problem, right? You try to solve problems, so you don't care the trivial root, because if a equal to 0, it will produce u bar equal to 0, and u bar is equal to 0. You talk about a medium without the displacement, so that is not the root that we are looking for. So now, if eta equal to 0 is not a root that you are looking for. So now you have to look at the system here that contains infinite number of roots. Now come back to this equation. How can we separate the two cases? The case that contains one root and the case that contains infinite number of roots. How can I separate the two cases? It depends on what? It depends on the condition of A. What is the condition that separates the two cases? Can you remember? We have to look at the determinant of A. If the matrix A here has the inverse, now this equation contains this equation have only one root. If A have an inverse, because if A has an inverse, you take inverse, you multiply equation by inverse of A. So this will become x and this becomes 0. So you have only one root. Okay? So if you would like to have infinite number of roots, determinant of A have to be 0. That's the only way that you can have infinite number of roots, right? Because if the determinant of A is 0, now you cannot get the inverse of A. So then this equation contains infinite number of roots. Okay, so now I would like to get the infinite number of roots here because I am not interested in the case that A is 0, right? So now I have to set the determinant of this one equal to 0. And you know that gamma here is still unknown, right? You can get gamma that make the whole thing here, the whole matrix here with the determinant equal to 0, right? Okay, that's the condition I'll set here. Okay, so this is the condition that I need to satisfy to get gamma, right? Okay, and this will allow us to get the non-trivial error, right? Okay. Let's say that I solve this determinant equation. I know matrix A, B, and C from the previous slide. I plug them in, and then I compute determinant of 2 by 2 matrix. You know how to do that, right? Do you know how to do that? Determinant of 2 by 2. Okay, so let's say that you know how to do that. So you combine all the matrices here, and then you set the determinant of the whole matrix to 0, and then you end up with this equation. So this is the final equation that you get by setting determinant of the whole matrix equal to 0. Okay, now you can see that you try to solve for gamma, right? So you will see that you have gamma square minus psi square here, and the whole thing here square, and you set that equal to 0. So now you have root like this, right? Gamma will be the absolute of psi and the negative of absolute psi, and you have repeated roots, right? Because you have square here, it means that you have gamma, 2 gamma with the same values here, right? So you have 2 repeated roots, and you repeat twice here, right? Is that right? Or you can say that this is the 4th order equation, right? Or you can say this is the polynomial of degree 4. You're supposed to have 4 roots, right? So the root that I talk about here, you have the root like this, the root like this, you have repeated root. So this is the root that you have for this equation. If you expand the equation, you see that you're going to get gamma square minus psi square like this, right? And square here. So you will get something like this. Right? So to get 0, so gamma have to be equal to this, minus this, minus it. So you can see that you have to repeat roots. Okay. So this is the root that we have. Because we have repeated root, so the multiplicity of each root is equal to 2, right? In this case. How can you get eigenvector? Now I know gamma. Okay, I have two different gammas, right? Two different gammas, and each one here we have repeated. You have multiplicity with 2, right? So you have repeated root like what I showed you here. Now I have to compute the eigenvalues. For each different root here, I can get eigenvector. Or what I try to say here, when you plug in gamma that you got here back into equation 3, now you can solve for eta. The eta you obtain by solving this equation for specific gamma that you got here. That eta is called eigenvector. Okay. So for this one, I plug in gamma 1 equal to the absolute of psi. I plug in this one back into this equation, and then I solve for eta. This is what I got. So there are details before you can get this one. You have to go back and try. Okay, you have to plug it in, expand them, and then try to come up with eta one. So if you guys already learned how to solve eigenvalue problem before, or even in dynamic class, right? You learn dynamic class, no? Okay, in dynamic class, you also learn how to solve for frequency, right? So solving for frequency is similar to solving for gamma here, and the eigenvector here is similar to the mode chain, the vibration mode chain. Okay. So let's say that okay, you know how to do this, okay? Because this is simply mathematics. Okay, I get eigenvector for the two different gamma, right? Gamma 1, I get eta 1 into that. Gamma 2, I plug that thing in as well. Okay, I get eta 2. Okay, I get two different roots, right? The root that I talk about, I have gamma 1 and have eta 1. So if you get gamma 1, you get eta 1, you plug it in here, you get one root. Because this is the root that you assume, right? This is the form of the root that you assume. Okay, but whenever you get gamma, whenever you get eta, you plug it in, you get root. So you plug in gamma 1 and eta 1 back, you plug in here. Now you get one root of that equation. Now you plug in gamma 2 here and eta 2 here, you get the second root. Okay, how many roots that you expect you have for equation 1? 4. You're supposed to get 4 different roots. How I know that? Look at equation 3. So equation 3, you expect to get 4 gamma. And actually you have 4 gamma. This is gamma 1, gamma 2, gamma 3, gamma 4. Or this that's right. Gamma 1, gamma 2, gamma 3, gamma 4. But you cannot differentiate between gamma 1 and gamma 3 because the gamma are the same. And gamma 2 and gamma 4 are the same. So now you get only 2 different rules. What happened? We cannot stop here, right? Because you know that this kind of differential equation, you need to have 4 different rules. So the plot here that I show you here is not sufficient to get all the rules. Now I have to get the 2 remaining rules that different from what we have here. For the general case, when you solve this kind of equation, you may end up with all different rules. That is the simpler case. Because if all gamma are different, now you can use the same process. Get eta for each gamma is different. Now you will get 4 different rules. But this is a special case, which is more complicated because you get repeated rule. So now you cannot get for the same gamma, you cannot get different eta, right? Because you have the same gamma. If you plug in this gamma back into equation 3, you cannot get 2 eta, you know what I mean? So this is the drawback of this technique. So now we need to find a way to recover the remaining 2. Okay, this is the way. Okay, how can I get this procedure? You can look in the mathematics book, okay, in theory of differential equations. Okay, I think you can look at the book in undergraduate level, and you should be able to get this kind of concept. Okay, if you believe about what I show you here, and you think that is sufficient to understand about the technique, then I try to recover the remaining rules.
I'm ready for your instructions.
Okay, you may not need to read additional documents. You can just simply follow what I put in the note here. Okay, so this is the procedure to recover the 2 remaining rules. Let's say that let's say that gamma is a repeated root. Let's say that gamma here is a repeated root. Let's say that I look at the gamma that corresponds to absolute side here. Gamma, I have 2 repeated roots. I already recover one, right? I already get either one with this gamma, right? It still remain 1 that I have to recover. How can I recover that? So this is the way that I will use. Okay. So before you say that let's say that gamma here is a repeated root, and you already recover one of them. Right? Let's say that this is the one that you already get. Similar to the previous procedure. For gamma 1, I already get the root associated with that gamma 1, right? How can I start from the one that I know to get the other one? Okay, this is the way. Okay? So I will seek another root based on the first root that I got. So let's say that this is the first root. Now I multiply the first root here by x2, and I add the term here. Okay, with the same gamma. Let's look at the way that I get u bar. This is the second root that I try to get. Okay, based on the first root that I have here, I didn't change gamma. I use the same gamma that I get here. Okay, I try to recover the remaining root. Okay, so I simply take the first root, multiply by x2, and then I add a term here. And the term that I add here, the exponential term is similar to that one, but I change the vector eta to low. Eta here is known already because I solved for eta before, right? But low here is still unknown. Okay, if I can determine this vector low, now I would say that I get the second root. Okay. So the work here, I need to get low. Whenever I can determine low, that make sure that this equation satisfy that equation. Now I will conclude that I get the second root corresponding to the same gamma. Because if you look at the form of equation 4, I didn't change gamma. I still use the same gamma, right? I use the same gamma. Okay, but the form of the solution that I assume here is not exactly the same as this one, right? You can say that I take the root that I know, I multiply by x2, and then add some term like this. Okay, so now how can we get the vector low here? The way that I will use to get this one, I plug in again the form that I shown here back into equation 1, and I will try to find that low here. If I can get low, now I say that I know the second root. Okay, plug in equation 4 into equation 1. This is the thing that I will get. Okay, so you take derivative of this term with respect to x2 twice, and this term with respect to x2 twice, you will get the like this. Okay, this corresponds to the first term there, right? Is that right? And I'm not sure, maybe you have to go back and try. I plug in this one, takes what derivative. Sorry, this may not be the first term. The first term is simply this one and that one, right? And then that one. Okay. Go back and plug it in and then you group the term. Now you get something like this. So this is the final result that you will get once you plug in u bar back into equation 1. Okay. What can I conclude from what I got here? What can I conclude here? What is this metric multiplied? What is this term? What is that term? 0? Is the whole thing here 0? Don't forget that gamma that I got here is the whole thing here. This equation have to be 0, right? Go back to equation 3 in the previous slide, right? Because gamma satisfies that equation, right? So the whole thing here have to be 0, so you can drop the first term. Is that right? Right? Okay. So now you have this thing left. And this one cannot be 0. So the whole thing here has to be 0. Is that right? Okay. How about that term? That term you know already, right? Gamma we already solved. Gamma we know. AB, the two matrices here are known. Error is known, right? Error we solved already, right? For this gamma we know error. So what I try to say here, the first term here is known. And the same inside here is known as well. Now I can solve for low, right? Because all the matrix that you have here is known. Okay, be careful, the whole thing here is not 0 because low here may not be equal to error, right? So that one is known. The matrix here is known. Now I can solve for low, right? So this is the way that I have to use to solve for low, right? Once you get low, once you solve low from this equation, now you plug it in here, now you get the second root. Is that right? Okay. Once I get the second root, now I can say that if you combine the two roots, so this is the first one that I recovered before, right? And this is the second root that I covered from here. So now you can see that for a repeated root, now I have two different for the same gamma, I have two different roots. The first root I got before, and the second root here I recovered by assuming in this form. Okay, so you can see that the plot here you just simply get low by solving equation 5. I will show you how to do that for our problem. Come back to our problem. Okay, let's look at the repeated root gamma 1. Gamma 1 equal to absolute sign. I already got one root for this case, right? I got A1 into this, so this is the first root that I got corresponding to this gamma 1. Now I need to get the second root. I need to get low 1 for this repeated gamma. Okay, this is the way that I have to do. I have to solve for low 1 from this equation, right? Okay, I move this term to the right hand side, and then I know this matrix, so I can solve for low 1. Okay, this is the example for our case, right? I plug in everything, plug in A, B, gamma 1, okay, to the left and to the right hand side. Now I have to solve for this vector. Okay, let's say that I solved it already, I got this one, O1. Okay, so this part is not very difficult, right? But it's required you to work out something here. Okay, solve for this for O1, vector to O1, get this vector. Okay, and the same thing for gamma 2. Okay, I have gamma 2 equal to minus sign, right? Minus absolute sign. So I already get eta 2 before. Now I get the second root or get lower 2 by solving this equation here. Okay. Equation that I have to solve here is similar to the previous one, except that I do gamma 2. Okay, and eta 2. Okay. So this what I got. I got lower 2 like this. Okay. Now we done, right? So now the general solution for this equation. Now we have 4 roots. This is what I got. This is the first one that I got before. This is the second one that I got before. Okay, I get this root and this root easily. But the second and the fourth one here that I got in this form, I got based on the procedure to recover the root when gamma is depleted. Okay, so now I get the complete solution of the displacement u bar. I already get 4 different roots. The first root, second root, third root, fourth one. Okay, and you can see that for each root I have the constant C1, C2, C3, C4. So the constant C1, C2, C3, C4 here are arbitrary constants. I have to determine all of them. Okay. Okay, this is the standard way to get the general solution for this system of ODEs. Okay. What do you think? Do you like the technique here? You don't like it? Compare with the previous technique. You think that the previous one is better, easier, but this one is more powerful, you know. And this one, you don't need to depend on what green functions. This one you can solve without knowing green function, right? So the previous technique, you can use the solution that I gave you whenever you know the green function, right? If the green function is not available, you cannot use the first technique, right? The first technique depends on the existence of the green function. For some particular problem, the green function may not be easy to determine before. So then, if green function is not available, the first technique fails. Yeah, this one will be better in that sense, because this one you don't need to talk about the green function, right? Okay. Now, up to this point, you get the u bar, you get the solution of displacement in the transform space. Don't forget that u bar here is not u. U bar here is the Fourier transform of u. Okay, how can I get back u? You have to do the inverse transform. But before we can do the inverse transform, how can we get C? Because we still have C1, C2, C3, C4 to be determined, right? Don't forget that we haven't looked at the boundary condition yet. Here we try to solve what? We try to solve this equation. We try to solve equation inside. Right? We try to solve the opening equation at any interior point. We haven't enforced boundary condition on the top surface. So okay, we have to do that to make sure that we can get C1, C2, C3, C4. Okay? To get all constant C1, C2, C3, C4, we need to apply the boundary conditions. Okay, this is what I will do. We have to enforce the boundary condition. And also here, because we have only one boundary, right? We have one boundary here, and we have two directions that we have to enforce the boundary, right? We have x1 and x2. So the traction boundary condition in x1 direction, x2 direction have to be satisfied. It seems that we have only 2 conditions, right? But we have 4 unknowns, constants. How can we enforce additional condition to get 4 conditions, to get all 4 constants C1 to C4? Now we have to think about what happened to infinity. Okay, if you, let's say that you apply loading only on the surface, what happened to to infinity. What happened to the displacement stress at infinity? What should we expect for the displacement? Let's say that the loading that you apply here is only localized in a small region on the surface. What happens if you look at point far away from that loading condition? What should be the displacement? What should be suppressed? It should decay to zero. Is that right? Physics of the problem tell you that when you move far away from the loading region, you should get smaller and smaller displacement, smaller and smaller stress as well, right? Okay. So you expect that displacement should be zero at infinity, right? Now go back to look at general solution that you got here. To make sure that the solution is bounded at infinity, which term that cannot appear in your equation? If you want to make sure that the solution is finite at infinity, because you cannot get infinite solution at infinity, right? It doesn't make sense at all if you apply the loading here, but you get stress and displacement equal to infinite at infinity, right? So which term that you have to eliminate it?
C1 and C3.
C1 and C2.
Right.
Because C3 and C4 you cannot eliminate because the exponential function with the negative exponent they will decay. When you can say that this one and that one decay when x2 getting larger. Right? When you look at the the displacement and stress far away from the surface here, so x2 getting larger and larger. What happened to the second? What happened to the first and the second term? Because if you look at the first term, you have the positive exponent. When x2 getting larger, this term will grow up to infinity, right? And this term and that term too. If you require that the solution should be finite or should be decay at infinity. So the first and the second rule cannot appear there, right? Because if they appear there, you have problem because you will see that solution at infinity will be infinite, right? So then I will get rid of that two roots because I enforce the boundedness of the solution, right? If I require that the solution have to be finite or decay to zero, so C1 and C2 have to be zero because if you keep the first two terms, you have problem. And the last two terms, you see that all the roots that we have there decay to zero when x2 getting larger and larger, right? Okay, so that satisfies our requirements. So now, by forcing the boundedness condition of the solution, finally we get u bar like this. We have only two terms, two roots, and now we have only two constants to be determined, right? C3 and C4. Okay, and also we have to enforce boundary condition, right? Regarding the load that we apply on the boundary. And we have two types of the load that we apply, right? We have normal force and we have tangential force. We have two conditions. So that should be enough for us to get C3 and C4, right? Okay, this is the way that I would use. Okay, we have, here I just simply expand the term that I have. So u bar is simply a vector of u1, u2. Now I can express explicitly in terms of u1 and u2 like this. Okay. Here, I get u1 bar and u2 bar in terms of C3 and C4 before I can enforce the boundary condition to get C3 and C4. You can see that on the top surface, we know traction, we don't know displacement. So here we know the general solution for the displacement, right? We cannot enforce the boundary condition through the displacement directly because we don't know the displacement on the surface, right? We know traction. Okay, so if you know the traction on the boundary, how can we enforce the boundary condition? We have to get stress first from this displacement. U1 and U2 that I got here, now I have to compute stress. Okay, how can I get stress? If you remember, in lecture 1, I already gave you the expression of stress in terms of the displacement, right? Okay, so this is the expression that I gave you before. Sigma 1, 1, sigma 2, 2, sigma 1, 2 in terms of the displacement. But be careful. The displacement you got at this step is the transform of the displacement. It's U1 bar and U2 bar. It's not the displacement U1 and U2 directly. This is the Fourier transform of U1 and U2. But the formula that I show you here is the formula before we transform. Okay, now what I will do, I will transform this equation first. And then I can plug in what I got here into the one that we transform. We can get stress in the transform space. So this is what I will do. Okay, I will transform this equation first. I apply Fourier transform to the first equation. I will get this. Apply to the second transform to the second equation. I will get this. Sorry, I forgot bar here. Can you add the bar there? So this should be sigma 2, 2 bar. Okay, so I get sigma 1, 1 bar in terms of U1 bar and U2 bar. Again, the derivative with respect to U1, with respect to x1, I change it to this one, right? I do the property of the derivative of the transform. Okay, so finally I get sigma 1, 1 bar, sigma 2, 2 bar, sigma 1, 2 bar like this. Is that clear? Okay, now you can just simply plug in. Second, I will correct this in first before I forget. Okay, so the next step, you just simply plug in U1 bar, U2 bar into the formula that I got here, right? So what I will get stress sigma 1, 1 bar, sigma 2, 2 bar, sigma 1, 2 bar, like this, right? So now stress component sigma 1, 1 bar, sigma 2, 2 bar, sigma 1, 2 bar in the transform space. So stress component that I got here is stress in the transform space. I transform first and then I get this in, right? So you can see that from U1 bar, U2 bar here, I plug it in, I get stress in the transform space in terms of C2 and C4. The reason that I have to do this because I don't have the displacement boundary condition on the top surface. I cannot enforce that kind of boundary condition to the displacement that I got there directly. So I have to get stress at any point first because when I know stress here, now I can check the boundary condition. I can force the boundary condition on the surface here, right? Because I know traction. Okay. This is the next step that I will do. Here, I will force the boundary condition on the top surface. Okay, you look at the top surface here. Okay, I know traction, normal traction, the green one, and the red one there. I have the shear traction. Okay, so the boundary condition that I have, this is the boundary condition, right? I can link the traction that I apply on the top surface and stress that I have, right? So stress, I take stress that I got before, multiply by unit normal vector to this boundary. The unit normal vector, outward unit normal vector pointing up. So the unit vector here will be 0 minus 1. So I take stress that I got before. I have to plug in x2 into 0 because I look at stress on the boundary, right? So x2 have to be 0. I take stress at x2 into 0 and multiply by unit normal vector. I will get this, right? I take this product, I will get this. And the thing that I got here have to be the same as the one that I described above. Or what I would say here, sigma 1, 2 will be negative T10, sigma 2, 2 will be negative T20. Okay? Sigma 1, 2 will be the same as the one we applied here. The negative of sigma 1, 2 because you have a normal vector pointing upward, right? And the negative of sigma 2, 2 will be the same as the green one here. That's the boundary condition. Okay? But the boundary condition that I got here cannot be enforced directly. This is the boundary condition in the physical space, not in the transform space, right? So the boundary condition that I got here, let me write down here again for okay. So okay. So the boundary condition that I have, I would have sigma 1, 2 at x2 equals 0 have to be equal to minus T10, which is a function of x1, right? And sigma 2, 2 at x2 equals 0 is simply minus T20, which is a function of x1. This is the boundary condition that they have. If you go back to look at the previous slide, I have sigma 1, 1 already. I have sigma 2, 2 already, but not in physical space. So what I have to do, I have to transform this one to the Fourier transform space, right? So I transform this one, I transform that one, I transform this one, I transform that one. So now I will get a condition that allows us to get a constancy. Okay, so this is the transform boundary condition. Okay, basically what I got here, just take transform of this condition. Okay. Now you can plug in sigma 1, 2 bar that you got in the previous slide. You plug in x2 equals 0. I'm not sure that it's clear to you. Go back to the previous slide. Okay, this one. Yeah. Okay, you can see that you get sigma 1, 1 bar. You just multiply the whole thing here by 2b. Sigma 2, 2 bar, you multiply the whole thing here by 2b, right? So what I will do, I need sigma 1, 2 bar here, right? And I need sigma 2, 2 bar here to satisfy that condition. Sigma 1, 2 bar and sigma 2, 2 bar have to be the same as the traction we apply. Okay, so then I will do this because sigma 1, 2 bar and sigma 2, 2 bar is set equal to traction. I have to plug in at x2 equal to 0. So I plug in x2 equal to 0 here, so this becomes 1. I plug in x2 equal to 0, this term drop, right? And that term becomes 1. I plug in sigma 1, I plug in x2 equal to 0 here, so this term drop to 1, and that term disappears. And that term drop to 1. Okay, so then what I got here is the equation that I got, right? So the first equation, I will get this multiplied by this plus this multiplied by this equal to something like this. So here's the final condition that I will get. I'm not sure it's clear to you. So I didn't show equation by equation like that. I plug in like what I did here, and then I prove that and put in express in terms of the metric like this. So now you can see that you have a system of linear equation. You have two equations. You should be able to get C3 and C4, right? Whenever you know T10 and T20 are. So T10 and T20 here is simply the transform of this loading condition. Okay, so this is basically the Fourier transform of the known function. So if I gave you this function, I gave you this loading condition. Now you can do the transform of the function. So similar to your homework assignment number 3, you can go back and try. I give you a linear function or quadratic function. You can transform them. In your homework assignment, t1 is 0. You have only t2, right? You can just simply transform t2 and put this equal to 0 and transform t2 more. Okay, and then once you get term on the right hand side from the given loading condition, now you can solve C3, C4, right? You finally get the two constants. Okay, so this is what you got. I solved the constant for you already, so this is the closed form C3, C4. Okay, once you're done, you get C3, C4 like this. This is the final solution that you have to do. Okay. From solving C3 and C4, you got this. You plug in C3 and C4 that you got before, plug in here, 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 here. What do you get? You get displacement U1 bar, U2 bar. The same for stress. Sigma 1, 1 bar, you plug in C3 and C4 from the previous slide, plug it in here, you get sigma 1, 1 bar. Sigma 2, 2 bar as well, sigma 1, 2 bar as well. Are we done here? Not yet. Because what we got here, we get displacement, we get stress, but we get in the transform space. U1 bar, U2 bar, sigma 1 bar, sigma 1, 1 bar, sigma 2, 2 bar, sigma 1, 2 bar are components of displacement and stress in the transform space. We need to get back U1, U2, sigma 1, 1, sigma 2, 2, sigma 1, 2, right? We have to perform the inversion, Fourier inversion. I have the formula for you already, right? You apply the Fourier inversion like this, right? This is the formula for the Fourier inversion. Plug this thing in here. You got it already with C3, C4 that you solve. You plug it in here. The same for U2, the same for sigma 1, 2, sigma 2, 2, sigma 1, 1, sigma 2, 2, sigma 1, 2. Yeah. But the integration here may not be simple, right? So you have to take the integration from minus infinity to infinity. Typically, you would not do it analytically. Performing the integration here to get the closed form is not easy. Because you go back and look, U1 bar here is quite complicated, right? Look at C3 and C4 that you got. As a function of sign, you can see that you have to take integration with respect to sign. I think that the integrand that we have to perform the integration here is not simple. It's quite complex. So it's not easy to get the closed form solution. In general, people try to get the value of the displacement spread based on the number of integration. So you have to perform this integration numerically. Okay, you can talk with your friend. Your friend used to do that before. Okay, in the thesis for the undergraduate level. So I asked him to solve some kind of problem like this using this kind of technique. So he needs to perform this kind of integration, but he cannot do it by hand for sure, I'm sure. But I should say that we have exceptional skill in mathematics. You may be able to perform the integration. But anyway, I cannot do that. I have to use numerical integration. Okay. We done here? So in this lecture, I try to solve half-plane problem under loading on the top surface. I propose you two techniques. Which one do you prefer? What is the drawback of the first technique?
Green function.
You need to have green function.
Yeah.
Right? Whenever you have green function, it will be easy. The rest is just simply take the integration, like the homework, right? I asked you to solve problem in the homework assignment number 3. You don't need to solve it again because you just simply do the formula that I show you, right? You just perform integration.
Yeah.
Okay. The second technique is also attractive. Okay, let me show you an example. Let's say that instead of have a half plate, now I have a layer like this, and I apply loading like this. Can you apply the first technique to solve this problem? How can I apply the first technique to solve this problem? This one is not half plate anymore, right? If you would like to use the first technique to solve this problem, what do you need to do first? You need to construct the solution of this problem, right? Right? And you need to construct the solution of this problem, right? You put the unit load here, right? If you can solve this problem, now you can use the first technique to get the solution of this problem, right? Use superposition. But the thing is, solving this problem now is not simple because your medium is not half plane. It's not infinite anymore in this direction. So it's finite. Solving for the closed form solution for this case is not easy. If you don't have the closed form expression for the green function, the first technique is not useful anymore. Okay? So now, how about solving this problem using the second technique? I don't need to do anything except that, okay, I can use the solution that we got before for this case because what I solved here, you can go back here. Up to this point, solution that I got here, displacement, stress. Did I say anything about the domain that I solved? I consider here. I did say that, okay, my domain have to be half plane. All thing that I assume x1 have to be range from minus infinity, right? I didn't talk about anything about x2 direction. I just assume that, okay, my body have to occupy from minus infinity to infinity. I didn't say anything about x2, right? So now if you want to solve this problem with the solution that they have here, you don't need to change this point. Now you just simply do what? You just enforce the boundary condition. You just say that, okay, for example here, you have four constant, right? Sorry, we can go back here. Sorry, we have to go back up to this point. We have to equal minus t to 0. You can see that this problem have four boundary conditions. This one. Now this four boundary conditions allow us to get C1, C2, C3, C4. Done. You can see that the second technique is also attractive for some problem. Now, actually this problem I asked your friend to solve in his thesis before, right? You solve this problem, right? But the problem is a little bit more complicated because he looked at the composite material. The material is not it's not homogeneous. It's homogeneous, but it's composite material. But anyway, now I can even make it more complicated. You can think about this problem. What happened if I have multi-layer? How can I solve this problem? Believe me or not, the solution that I derived for you here, you can use to solve this problem. Because if you look at this layer, this solution works well for that layer. You look at this layer, the solution here works well too. Let's say that, okay, if this one I use mu and kappa, mu1 kappa 1 is mu2 kappa 2. So you can still use the same solution that I got here, right? You just simply change the material property. The general solution that I developed here can be applied for each layer. Okay, so you can apply a solution here, and then you can connect them using continuity. Okay, you can go back and think about that. So the second technique here can be applied to this kind of problem as well. Okay. But I will not show you in this class. I just try to point out the advantage of the technique that I use to solve half-plane problem. Okay, if you are interested in, we can discuss more separately. Okay, if you would like to. Because I asked the student before to solve this kind of problem when the medium is nanoscale. It's still medium with nanoscale material. That we have, if you think about a problem that you do the coating. Let's say that it's the object, we do the surface coating. But we can coat the object with several layers, right? You can think about the pan. You know pan, right? So you have the coating on the surface to prevent the damage on the surface of the pan when you do the cooking. Okay. You can coat with several layers of material, and the layer is very thin. So the material is quite complicated because you have to model material in a small scale. But the technique, like what I consider here, can be used to apply, can be used to solve that kind of problem. Okay. That's some of you here. We haven't finalized the topic for your research, right? We can think about several possibilities. Okay, there are several possibilities that we can do. Okay, if you like to solve challenging problem. Okay, I can come up with something challenging for you guys. Yeah. Okay, we're done with this lecture. Do you have any question about anything? Any questions? I will give you a break for 10 minutes, so we will come back with. Okay, let me show you this lecture first. I will look at the half plane again, but the excitation is more complicated here. So this is the problem that I will look at. Now I will.
มันไม่โชว์ครับมันไม่ขึ้น
Okay, sorry. I will look at this kind of problem now. We look at the half plane again, but now the excitation is not the loading. I will not put the loading directly on the surface. I will put the contact like this. I compress the half plane by a punch or indenture. So I may apply the force here. Let's say that I apply the force there, but I don't know the distribution of the force that transfer to the half plane. This one will be more complicated, but it's more realistic, right? In reality, when you talk about the contact between two bodies, you don't know exactly the load that you transfer there. You always have in the form of contact, right? Typically, when you look at the foundation problem, when you have a foundation, let's say okay, the load transfer directly from the column to the foundation. If you don't have eccentricity, you assume that the loading there distributed uniformly, right? On the surface, on the contact surface. Is that true? It may not be correct. You know what I mean, right? But we always do that approximation all the time to simplify the problem. But the correct way to get the distribution, we have to solve this kind of problem, right? We have to look at the contact and now try to evaluate the pressure under the contact, right? The distribution may not be uniform. I will show you how to do that on this problem. It's a little bit more complicated than the previous problem. Okay, we will come back and talk about this. I will give you a break for 10 minutes. Previous lecture. Okay, we look at the half plane made of homogeneous isotropic linear elasticity well. Okay, so we have only two constants to characterize the property of the medium, mu and kappa. Okay, I can change the problem to be more, complicated. For example, I can make the material here is non-homogeneous. I can say that we have several layers, you can make things more complicated. But anyway, the technique that I will show you here, you can exchange to solve more complicated problems. Okay, so here for illustration, I try to consider the simplest case, and this will not limit the applicability of the technique that I will show you here. Okay, you can always apply this kind of technique to solve more complicated problems, like a layer medium or multi-layer medium like that. Okay. So here, in this lecture, we focus only on this simple case. Okay, x2 here, the medium in this direction, x tends to infinity. Okay, we don't have the boundary in here. I say here. So we have only the boundary at the top here. Okay, so in this case, let's say that the half plane is indented by the rigid, frictionless indenture. So the indenture here is rigid. What do we mean by rigid? It cannot deform. Okay, the indenture here cannot deform. Okay, it's rigid, no deformation, no strain, no change in shape. Okay, no distortion when you compress the half plane. This this indenture contains no deformation, what I would say. And it's frictionless. It's frictionless, it means that the load transfer to the half plane, you have only normal component. Okay, when you contact, you have the contact, no friction. I assume that there is no shear traction. Okay, is that correct in real problem? For the actual problem, this assumption may not be correct. Because for example, if you have the surface like this, and let's say this is your indenture, place it. You may have shear attraction generated here because you have friction. You can have friction there. It depends on the smoothness of the surface, right? So in this case, I just simply look at the simplest condition. Okay, the indenture is rigid. Actually, if you look at this indenture, is that rigid? Do you think? No. When I compress it, this can deform as well. Not only this one that deform, this one can also deform, right? But for simplicity here, I assume that this one is made of material that have larger, sufficiently larger modulus. Okay, so then the deformation of this one is much smaller than the deformation of the medium here. So then I assume that the indenture is just a second, let me take the phone call here. Sorry. When I compress the half plane by this indenture, we have the known contact length. Let's say that the contact length is equal to 2a. This is known a pi of it. For example, let's say that I have the width of the indenture like this. I compress it. I compress until I make sure that I ensure that the contact here is equal to the width of the indenture. So the contact length is known a pi of it. It's not unknown. But for some particular case, let's say that I have the spherical indenture. I compress it. So you don't know the contact length of pi of it, right? Because if you have, let's say that this is the, you can take a look at this, the contact here. So if I put the force larger and larger, the contact length getting larger and larger. Okay, that is not the case here. So I assume that the contact width here is known a pi over e. Okay. Don't worry. For the problem that we don't know the contact length, I will solve it later because it's more complicated. I will solve the simple case first. In this case, I know a contact length of pi over e. Okay. Let's assume that when we apply the force to the indenture. Okay, we compress the half plane by the indenture. The force that we apply to the half plane through the indenture, we have the magnitude of the force equal to P, and the line of action of the force doesn't align perfectly with the centroid of the indenture. Okay, the centroid of the indenture is at the middle of the contact region. Let's say that the load that I apply here have the eccentricity equal to E, measured from the centroid of the contact region. Okay, or the mid, the center line here. Okay, so the line of action doesn't align with the center line of indenture. We have the eccentricity equal to E. Okay. So in this case, you can think about it. The indenture will tilt a bit, right, depending on the distance E here, right? Okay. So you have the rotation of the indenture. Let's say that okay, the indenture profile here can be arbitrary. I will solve the problem with any kind of profile. Okay, I will give you this profile. I give you this function delta. Let's say that delta here that I use to define the profile of the indenture. Okay, delta here is a function. Okay, delta here is a function of position along the line here. Okay, so delta here can be any function. Okay, the only thing that I assume here, the delta here have to be sufficiently small to make sure that okay, when you apply the force from the indenture to the half plane, the deformation is small. So delta cannot be very large. If delta is very large, so you have a significant slope, so that will generate deformation that is not small. Okay. That assumption is reasonable when you think about. So this, let's say this is a half plane. When you compress it, did you see any deformation? Okay. In this case, you cannot apply the indenture that have a profile like this, because if you compress like this until you get the full contact, now you have large deformation of the half plane. That kind of problem I will not focus on here, because in that case, the deformation will be significant, and the linear theory cannot be applied anymore because the deformation is very significant, right? So I just simply look at the half plane that have infinitesimal deformation. So then the profile of the indenture cannot be very large. The distance delta here cannot be very large. Okay. So all I can say that we have the shallow profile for the indenture. Okay. Do you have any question about the description of the problem here? Any question? This assumption. Do you have any problem with this assumption? I assume that okay, delta over A. This distance over A is small, and also if I change derivative of delta with respect to this coordinate is small too. So what I try to say, the slope of the profile should be small. Okay, this kind of information is okay if you deal with the shallow, the indenture with the shallow profile. Okay. Okay. Is that clear for the description of the problem? Okay. I look at the half plane. This is example of the indenture. You compress it like this. You get a full contact over the length 2A, and the force that applied here can have eccentricity. So you can have the rotation of the indenture as well. Okay. That's the problem that I'm looking at here. Okay. What I try to solve here, I would like to know, once you compress the half plane with this indenture, with the force like that, what is the displacement? What is the stress that you induce inside at any point x? That's what you are trying to get. This problem getting more complicated, right? Compared with the previous one that you solved. solved before. How can we solve this problem? Do you have any suggestion? If you think about the thing that I showed you before, I solve this problem. I will go back and look at previous problem I solved, and then I try to use the result of the previous problem to solve subsequent problem, right? Okay, I have a reason why I solve half plane under the survey load first. I hope that when I complete solving half plane under surface loading, now I can use the result from that case to solve this problem as well. How? How can I do that? I would not go back to the original state. Okay, someone said, why don't we go back and pick V from our pocket? Pick appropriate choice for the array state function and use that to solve this problem. You can do that, you can try, but it will not be easy, really. Okay, so I will not go to that step and start from zero like that. Okay, I will try to use the result that I got before. To solve this problem, I will use the result from the previous lecture. I will use the result for the case that I have surface load applied on the half plane. Okay, how can I do that? This is the way. I will use the method of green function. First, I will sketch the free body diagram of the indenture and the half plane. Okay, so I separate the two, and then I sketch the free body diagram for each part. Okay, so the thing that we don't know is the pressure under the contact region, right? That's the unknown that we don't know. The thing that we know the resultant force. I told you that I compress the half plane by the indenture with the force P. P there is known. I know for example, I apply the force, I know that I apply the force, let's say that I apply the force 10 kilonewton. I know the force that I apply 10, but I don't know the pressure down here. I don't know how 10 kilonewton here is, I don't know how it distributed on the surface here, right? So the pressure here, I don't know exactly how this distribution can be described by any function. I don't know at this point. So P is unknown function, right? The only thing that I know, if you compute the net force of the pressure here, it has to be equal to P, right? For equilibrium. So the net force here has to be in equilibrium with the force P that you apply. And how about the pressure on the half plane from Newton Earth law? You know that this one and that one have to be the same, right? Action to reaction. Okay. The thing that makes this problem difficult is what? P is unknown. That makes things difficult. If I can solve for P, if you look at half plane problem, is that different from the problem you solved before? If you know P, if someone solved this problem and gave you P, you look at the half plane problem, is that different from the problem you solved before? No, right? Whenever you know P, you can say that the half plane problem is under surface load, right? But the problem is P is unknown. But anyway, let's say that I assume at this point that P is known. Can I solve this problem in terms of P? If let's say that P is known, now I can solve this problem in terms of P. Okay, I can get the solution in terms of P, and then I will try to force the condition at the contact here to solve for P. I'm sure it's clear. Let's say that forget about the top part. If you solve this part, can you solve the problem here? Okay, you can solve it, right? Okay. let's say that I don't know P a priori. If you don't know, can you do trial and error? Maybe you assume P, one function P. You're done with solving that. How can you check whether that P is correct or wrong? How can you check it? Okay, let me give you a simple example. Okay. I gave you this simple example, and I would like you to do the test in you imagine about the test in your thought process. Let's say that this is the applet. I have a flat end indenture. Flat is the simplest one that I can have, and I can apply the force at the center like this, no eccentricity. Okay. I solve this problem. Now I don't know how the pressure distribute along the contact length. I don't know, but I know that okay, the resultant of the pressure have to be UP. Is that right? Okay. Let's say that I don't know. I assume that okay, the force is uniform. Let's say that this is 2A. Let's say that this is simply P over 2A. I assume this. So that will be in equilibrium with the force P, right? How can I know that this one is correct or wrong? How can I know? Do we have a way to test that this one is correct or wrong? How can I check that? How can I check that? That's one the thing that I assume there. How can I check that? If I say that okay, I don't know, I assume that okay, the pressure is uniform. How can I know that that one is correct or wrong? Do you have a way to test that? Do you have a way? Can you solve the problem down there? This problem, can you solve it? I solved it for you already in the notes, in the previous slide, in the previous lecture, right? I solved this problem for the uniform load like this. If you think that okay, that this one is not correct, you can change to something else. You can change this to this one as well. If you think that this one is not correct, why don't you change it to this one? How can we check that this is correct? This one you also solve in your homework assignment. Right? How can I check that okay, the thing that I assume here is correct or wrong? How can you assume? How can you check? If you know how to check, now you know the technique that we use to solve this problem. Okay. Let's do it this way. When you solve this problem under the uniform load, can you get the displacement on the surface? Can you get the surface displacement? Can you get the surface displacement in the vertical direction? You can get U2, right? Let's say you plot U2, you get something like this. If the uniform pressure here generate the surface displacement like this, do you think that is this the correct answer for a whole problem? No, because you can see that we have the contact like this. So this one will not make the complete contact. So this one is not correct. Right? Because you have a gap there. Because when you compress like this, you need to have a full contact here. One way that I use to test that okay, the thing that I assume is correct or not, I solve this problem and then I check the displacement in the two direction and check that okay, over the contact length 2A is the displacement uniform. If U2 here is uniform, the same for every point, now you can contact with the flat end indenture here. Now you can say that pressure is correct. Is that right? But for sure, I will not do a trial error because there is an infinite possibility, right? Infinite number of possibility of the pressure, right? It's very difficult for you to guess until you get the perfect match between the displacement and the profile of the indenture, right? So trial and error is not a way that I would use here. But the compatibility between the movement on the surface and the profile of the indenture will be used to find a way to get the pressure P. Okay, is that clear? Okay. Now, I will try to develop a technique based on this idea. Okay, based on this idea. First, let's say that okay, P here, I assume that P here is a functional sign, and P here is unknown function. It's unknown. I don't know the form of the function P. It's unknown. I will determine the correct form of the function P. Okay, it's unknown. Okay. In this problem, I will choose the pressure here as the key unknown or primary unknown. Okay, I will choose the pressure as the key unknown. Whenever I can solve for pressure P, I would say that I'm done with solving the problem, right? Why I can say that? Why can I say that? If I get the pressure, can I say that I am done with solving problem? Because whenever I know P, I can go back to the previous lecture. When I know P, I plug in P there. I can use the formula. I perform integration like what you have to do in your homework. Whenever I know P, I would say that again, I can use the result from the previous lecture to get anything inside the medium. So my target here is to solve for P. Whenever I get P, I would say that I'm done with solving this problem. Okay, so P is my primary unknown. Okay. Okay. Here, I start first by looking at the condition for P. What should be the condition for P? P has to satisfy some condition, right? And the condition like this have to be satisfied as well. What else? Besides the condition like this, what else do I have to satisfy? If you look at the 4P that you apply and the line of action of the 4P, so the pressure here have to satisfy equilibrium of the indenture. Or I would say that the pressure that you have here have to be in equilibrium with the 4P. Okay, so this equilibrium have to be satisfied. So when you perform the integration to get the net force from the pressure, you have to be into P. Is that right? You integrate the whole pressure here, you have to end up with the net force into P. If it's not the same as P, this indenture is not in equilibrium, right? The force that you apply and the pressure have to be you have to get the balance of the force, right? So force P and the integration here have to be the same. What else? You need to think about the moment equilibrium as well. You take the moment about the center line here. The moment due to the external force should be P multiplied by E. And if you take the moment of the pressure about the center line, you have to perform this integration, right? So you take P multiplied by the distance here, side here is the moment arm of the force P, of the pressure P, right? So this integration will represent the moment about this center line. That moment have to be equal to P multiplied by E. You can think about that term on the right hand side of the two equations here. External force and external moment. And on the left hand side are simply the moment and the net force produced by the force P. They have to be the same for equilibrium. Okay. So this is the condition that the pressure have to satisfy. But these two conditions are not enough. If we satisfy only two here, you can see that this one satisfy the two conditions here, right? If I apply the 4P like this one satisfy the two equilibrium equation, but they are not enough, right? This one is not it's not an answer for this problem because even it's satisfied equilibrium with the fault P, but you may violate the condition under the contact region because you may have a gap there. Okay. Now, I will look at the additional condition that I have to enforce to make sure that the fault P is the correct one. So the fault P that I apply here need to generate the deformation, or the fault P, the pressure P that I apply here need to generate the surface displacement that consistent with the profile here. Is that right? Or I would say that the displacement profile over the contact region, the displacement profile here have to fit perfectly with the profile of the indenture. In that case, you don't have the gap, you don't have the overlapping, right? Okay. So this is the condition that I will try to enforce. First, based on the fault P here, if you look at the half plane, I apply the traction like, I apply the pressure like this. So you can see that for this half plane, there is no shear traction. Based on the assumption that I made at the beginning that we don't have friction. So this half plane is subjected only to the normal traction T2, right? So T2 is simply P here. If you go back to the previous lecture, if I apply the force in the normal direction, the displacement on the surface can be obtained from this formula, right? This is not new for you, right? Go back to the method of green function in the previous lecture. If you would like to get the displacement on the surface in the two directions, you just simply take the green function U22 multiply by the traction in the two directions, because the traction in the one direction is 0. So you take the surface displacement green function multiply by the force P that you have here, traction P that you have here, and you perform the integration over the surface here, and because you apply the pressure only on the contact region, so you take the integration from minus A to A. Okay, this is not a new formula. You saw it before, right? Okay, and I use the superscript HT here to emphasize that this is the displacement for the half plane. Okay, this is the displacement for the half plane. HT here stands for the half plane. Okay, U2 here is the displacement on the surface. The displacement on the surface of the half plane. Okay, I can compute it from here. When I plug in U22, because U22 is a green function. U22 here is a surface green function of the displacement of the half plane. I have an expression for U22, right? So I plug it in, and this is the final integration that I have to perform. Okay. Okay. Now, if you assume that the pressure like this, you can just simply plug in a pressure here, right? And you perform the integration, you're gonna get the displacement like this. Okay? Whenever you assume the pressure, you can plug it in that formula, perform the integration, you will get the surface displacement. Okay? But I will not do that. I will not assume one by one and check. Okay? But I will put in this, I'll put in the integration like this. I will say that again, the whole thing here is simply the displacement U2 on the surface of the half plane. Right now, we go this way. Okay. Now you look at the indenture. Okay. Look at this. This is the final stage. Once you compress the half plane by the indenture, right? So this is the final stage. can see that if the pressure that you got is correct, you will see that there's no gap, there's no overlapping over the contact length 2A, right? From the previous slide, the displacement of the surface of the half plane, so the displacement U2, you measure from the original line here to the surface here, you get U2 HP already from the previous slide. So the formula to get the displacement of the half plane, you use the formula that you got before. Now, if you look at the displacement of the indenture, it should be the same, right? If you look at every point on the contact region, the displacement U2 of the half plane and the displacement U2 of the indenture have to be the same, right? If they are different, what happens? You will have a gap, or you have overlapping, right? If U2 of the half plane is larger than U2 of the indenture, you have a gap. If U2 of the half plane is smaller than U2 of the indenture, you have overlapping. You cannot accept both of them, right? The only thing that you accept, the two have to be the same, right? Okay. Now, I already have the formula for displacement of the half plane. How can I get the formula for the displacement of the indenture? Let's say that again, the indenture here, I know the profile, right? I know the profile. And let's say that again, the indenture, once I compress it, let's say that okay, the center of the indenture drop with the distance d0, and d0 is not known here, right? It's unknown. Let's say that okay, I compress, you can think about that. I compress it. Let's say that the center here drop with the distance d0. d0 here we call it indentation depth. That is the indentation depth. The d0 here depends on p, right? If you put larger and larger p, d0 will be larger, but d0 is unknownable. Okay. And also, because you have a force p that apply eccentrically, so now the center line of the indenture will not align with the vertical axis anymore. It will tilt a little bit. Think about that. If you apply the force p like this, because the force p is at the center, the line of action of the force p align with vertical line. So when you compare it like this and the profile is symmetric, you will not have angle failure, right? In this case, angle failure is 0. Now what happens if you apply the force p that is aligned with the vertical axis? We have the force p like this. You have the eccentricity. What happened to the indenture at the final stage? It will tilt a little bit. It will not move in a vertical direction like this. It will not translate directly. You will have a rotation. And the rotation is also unknown. I call it the angle theta. The angle theta there is the rotation of the indenture. Okay, now I would say that the indenture, because the indenture is rigid, right? If I know the translation d0 or the indentation depth, and I know the rotation, can you tell me exactly the displacement on the profile? I will know that. Okay. Can you tell me the formula? Look at this thing first. If I say that okay, your indenture move down with the distance d0, and then it rotate a little bit like this with the angle here equals theta. Can you tell me what is the distance of each point along that line? Let's say that the angle theta here and d0 is small, right? Because we look at the deformation that is small. Let's say that if angle theta is small and the indentation depth d0 is small too, can I say that the displacement of the indenture take this particular form? Do you believe it? The displacement at any point here consists of 3 parts. The first part, d0. The second part, it comes from the rotation. And you look at the first part, d0 is uniform everywhere. You think about that, you shift this thing down. You shift this thing down equally with the distance d0. And then you rotate. The rotation will make the displacement linear. Because if you move far away from the point of rotation, the displacement getting larger, right? So it's linear. So that's why the second term is linear. You take angle theta and multiply by the distance. So it represents the linear part here, right? So you can think about that you drop this indentation down a little bit. So every point moves in the same way. And then you rotate with the angle theta. So now the second part here, you have to add the linear term. How about the third part? Because the third part involves what? Profile. The thing that I look at here, I don't have the profile because it's flat and delta is 0. Now, if delta is not 0, you can think about this. You can think about the profile like this. Okay, so now you have to look at the profile like this. So now you have to add the thing that associated with the profile as well. So the profile, the distance delta that describe the profile have to be superposed into this. So now you can say that the displacement U2, the vertical displacement of point on the indenture can be described by indentation depth, rotation, and profile. Typically, the profile is known up highly because I give you the profile of the indenture for sure. For example, for this case, if you have the flat end indenture, delta is 0. Okay? But d0 and theta are unknowns up highly. I have to determine. So this is the form of the displacement in the vertical direction of the indenture. This is U2I. Now, I need to enforce the condition for the full contact over the contact length to A to ensure the full contact, to ensure that we don't have the gap, to ensure that we don't have the overlapping of the material over the contact length to A. I need to set or I need to force the condition that U2 HP and U2I have to be identical, right? At every point along the contact region. So U2HP, this is the surface displacement of the half plane. This is the displacement at the point on the profile of the indenture. Okay, the two have to be the same. And they have to be the same for all points. For all points. For all points between minus A to A. Not some point, for all points. Okay, to make sure that everywhere here, you didn't see the gap, you didn't see the overlapping. This is the condition that you need to enforce. So now we plug in U2HP that you got before and U2I that you got here. So this is the equation that I have to enforce. Okay. Now equation 2. Complicated, right? To make this problem a little bit easier in the calculation, and d0 that I have here, it's difficult to get d0 because d0 here involves some shift of the displacement in this direction, so it somehow involves digit body motion. How can I get rid of this d0 from this equation? I take derivatives. I take derivative of this equation with respect to x1. Okay. I take derivative just simply to eliminate d0 from the equation. Okay. So taking derivative will not change the meaning of this equation, right? So you can think about this. If you know the displacement, the derivative of the displacement is simply the slope of that, right? So if you take derivative here, you just simply enforce the slope have to be the same, right? So it doesn't change anything because if the two curves there are the same, slope have to be the same too, right? Okay. So I will use the equation 7 instead of equation 6 because I try to eliminate d0 from this equation. And also when I take derivative with respect to x1, okay, this integration, you take the integration with respect to side, right? When I perform the differentiation with respect to x1, I can move derivative inside and take derivative of this function with respect to x1. Okay, so that's why derivative of log function now become this function, and the absolute sign disappear because of that differentiation, right? Okay, so the sign inside here become this one because I take derivative of the log function. Okay, and the negative sign disappear because we have this x1 minus sign, right? So I just switch the sign here, you see that. Okay. Okay. So now I have enough equation, right? How many equations that I have here that cover pressure P? I have 3 equations, right? The first 2 are simply equilibrium of the indenture. And the last one here is simply the compatibility of the displacement of the 2 parts here. Okay, this simply, I call this one the compatibility or the consistent condition for the displacement of the indenture and the displacement of the half plane. So they have to be consistent to prevent the gap or material overlapping. Okay? Okay. So that's the condition that I need to enforce. Okay? How many constants that I have left here in the equation? Can you list the equation again? The first equation that I have equilibrium equation of force, right? I have the integration of P, right? I take the integration from minus A to A of P as a function of psi. I take the integration with respect to psi, and that has to be equal to P, right? So that's the first equation. And the second equation is the moment equilibrium equation, right? So I have this, and that has to be equal to P, right? Right? And the third equation is that one. Kappa plus 1. Right now, take the integration of 1 minus A to A of P, which is the function of psi, and divided by psi minus x1 d psi, right? And that has to be the same as theta plus the theta by the x1. Okay, and this equation have to be satisfied for all x1 from minus A to A. Okay. I have 3 equations like this. How many unknowns that involved in these 3 equations? I have 2 linear algebraic equations, and I have this. What should I call this equation? Integral equation. This is integral equation. I call this integral equation because the unknown is inside the integral. P is unknown. This is not differential equation. If you talk about differential equation, you talk about unknown that is embedded in the differential operator, right? But this one is not differential equation. This is integral equation because unknown sit inside the integral. This one is more complicated to solve, right? Compared with the differential equation, right? But you think the differential equation is already difficult, right? It's already difficult. But integral equation is even more difficult to be solved. But anyway, don't worry, I will teach you how to solve this one. Okay. First, we have 3 equations. We have 2 linear algebraic equations, right? And 1 integral equations. Okay, How many unknown do we have here? We have P as function of psi, right? So this is a function that we have there.
Okay, yeah.
Before we have D0, right? Okay. Right, before we have D0, but I get it off that from this equation. I think that we have enough equation to solve for that one here. Right? We will try to solve that. Okay, how can we solve that? I think that I need something from the node that I upload in my course field, right? I give you additional note about Chebyshev functions. I'm not sure that you already look at the node that I upload in my course field. I have two additional nodes, right? One for Buckingham pi theorem and one for Chebyshev functions. I will use that Chebyshev function to solve this problem. Before I solve that equation, I will try to make it. I will try to express the equation 3 here in a form that more appropriate. First, I will try to normalize all the quantity that appear in that equation to make sure that each quantity contains no unit. Okay, if you take a look at the quantity that I have here, for example, the coordinate psi and the coordinate x1 have a unit of length, right? To normalize that, to make sure that we don't have units, so I will normalize x1 by a. I divide the coordinate x1 by the half contact length a. So now I call that x1 bar. So x1 bar is simply x1 over a. So now x1 bar has no unit, right? And if you look at coordinate of point under the contact length, okay, now you can see that x1 bar raised to minus 1 to 1, right? Before x1 raised to minus a to a. Upon normalization here, so x1 bar raised to minus 1 to 1. Okay? I do exactly the same way for the coordinate sign. We have the coordinate sign here. Okay, side there is the point inside as well. So I normalize the same way. So side is normalized by a. So you can see that side bar here we use to describe the pressure, right? So the pressure under the contact length, so side bar will range from minus 1 to 1 as well, right? Okay. E bar. E is simply the eccentricity, right? You can see that we have the eccentricity here. E have the unit of length. So now I normalize E by A as well. I call that E bar. Okay, now E disappeared from here. I normalize by A. Okay, so now we have E bar. What else? P. What is the unit of P? What is the unit of 4P? P here have the unit of force per length. It's not the unit of force because this is 2D problem. We have the thickness as well. So the force P that we apply here is a force P per unit length in the thickness direction, right? So P here have the unit of force per length. So now I normalize by mu A because mu have the unit of force per length square, right? I multiply by A, so mu A have the unit of force per length. So I normalize P by mu A. So now P bar that I define this way has no unit. Okay. And also this constant, kappa, we don't have the unit, right? Kappa. I define kappa plus 1 over 4 pi. I just simply define this quantity as lambda for conciseness. Okay, I just term the thing here equal to lambda. So now, based on this normalization, also I have one more profile delta, right? We have the profile of the indenture described by the function delta. And delta here is simply the distance, have the unit of length. So I just simply normalize delta here by A. So I normalize by this. And also before delta here is given in terms of x1, right? So now delta is given as a function of x1 because x1 is normalized like this. So before it's a function of x1, right? So now I have to replace x1 in this function by A multiplied by x1 more. Delta is given as a function of x1, and x1 is simply x1 bar multiplied by A. Okay, so I have to change delta, the original delta, as a function of x1 to a function of x1 bar, and then I normalize by A to make sure that delta has no unit. Okay, that's the way that I did. And then, based on this, P as well. Sorry, I have one more. The pressure that is the key unknown here. The pressure have the unit as well, right? I normalize by mu because the pressure have the unit of the same unit of stress, right? For per area. So I normalize by mu that have the same unit. So now P bar have no unit. Before P that we have here as a function of psi. Okay, I change from a function of psi to a function of psi bar by simply replace psi by psi bar multiplied by A. So this is the way that I normalize P bar. Based on this normalization, now equation 1, 2, and 7, or equation 1, 2, 3 on the board here. 1, 2, and 7. I should change it to 7 so to prevent the confusion, right? So I have 3 equations here. 1, 2, and 7. Upon the normalization, the equation will change a little bit like this. Okay, you can see that the first one, I simply change P to P bar, and our function and the psi there is replaced by psi bar already, right? So I take integration from I change from minus A to psi, minus 1 to 1. Now I perform the integration over psi bar, not psi anymore. And on the right hand side, I deal with P bar and P. Okay, you know how to do this, right? This is just simply the normalization. The normalization is simply multiply or divide equation by a constant, right? I just multiply or divide the equation by a constant to make sure that the quantity that is more there contain no units. That's all. Okay, so I get equation 2 in this form due to the normalization. The same for the last one, right? So this is the final equation, the final form equation that I have to deal with. Now everything that involved in this equation has no unit. Okay. Now we should be ready to solve the whole system here. If we can solve the whole system here, we expect to get P bar. Okay. Do you have any idea how to solve this problem? Do you think it's easy? If you have to solve differential equation, you have some idea, right? Because you learned how to solve differential equation before, right? I gave you ordinary differential equation. You learn how to approach, how to get the solution, how to approach the problem, how to attack the problem, But here we involve the integral operator, not the differential operator. So it's quite new for you guys. Okay, I will show you how to do this for this particular type of integral equations. Okay. One thing that I would like to point out. If you look at the term here, do you think that this integral have some difficulty? Because this equation have to be enforced for x1 bar inside this integral, right? So, sorry, this is wrong. Can you correct this? x1 bar should range from minus 1 to 1. So that is wrong. I will correct that as well. Okay. Equation 10. The range of x1 bar It should be 4 minus 1 to 1, not minus 8 to 8 and so on. Okay? Correct that. Okay, you can see that x1 bar in that equation 10. In the equation 10. It's range from minus 1 to 1, right? And how about sine bar? Second, I will pick up this ball. Sidebar, you take the integral from sidebar equal to minus 1 to 1, right? You can see that sidebar and x1 bar can be the same. Let's say that when you perform this integration, if I fix x1 bar, let's say that I fix x1 bar equal to 0.5. So now you have a problem with this integration because if you take the integration from minus 1 to 1, you change sidebar from minus 1 to 1, you will find that when sidebar equal to 0.5, this one and that one will be the same. Now your integrand will be infinite at that point. So this is the difficulty of this integration because at some point this integrand will be singular. Right? Whenever sidebar equal to x1 bar, now this one roll out to infinity. Okay, that integral we call Cauchy integral. Okay, it's singular. And how can we perform the integration with the integrand that go up to infinity at some point? Let's say that I ask you this question, can you answer this question? Take the integral of 1 over x minus 0.5 dx x from 0 to 1. Can you perform this integration? What kind of function did you perform that we integrate here? If you draw a graph, here you try to get the area under the curve from 0 to 1, right? Okay, what kind of function that you integrate here? At 0.5, what happened to the function? The function will look like this. Is that right? This is the function you try to integrate. Right? You may have not 0 here, you may have somewhere here. Right? Right? You can see that when x is less than 0.5, you get negative. But when x approaches 0.5, it's go up to minus infinity, right? The same when x is larger than 0.5, okay, it's positive. But when x approaches 0.5 from the right, it will grow up to infinity. How can you get the area here? This is difficult. Okay, this kind of integral, we cannot interpret the value of this integral in ordinary sense. In the sense of Riemann sum, it doesn't work. To get the value of this integral, we have to interpret this in the sense of Cauchy. So this kind of integral we call Cauchy singular integrals. Okay? But anyway, I will not talk in very detail about that kind of integral. Okay, so if you are interested in, I can discuss with you in more detail separately. Okay. So now, before we solve this equation, I will use the function, the special function we term Chebyshev function. I think I should stop here and let you guys to read or review that kind of function first. Okay, maybe you have to go back and read the note that I gave you in addition. So this is the part that doesn't involve mechanics. It's just simply the mathematics. Chebyshev polynomial. It's simply a family of polynomials that satisfy some basic condition. Okay. We honor Chebyshev. Chebyshev is a mathematician. He invented this kind of polynomials. Okay, it's just simply polynomial. But this polynomial has some special properties. And I will use this property later to solve this equation. Okay? So the Chebyshev polynomial, there are two kinds of these Chebyshev functions. Okay, we have the first kind and the second kind. The Chebyshev polynomial is defined over a domain for minus 1 to 1. This polynomial is defined over an interval minus 1 to 1. So this is one reason why I have to normalize equation. I normalize the coordinate. Okay, for example, sine x1 before it range from minus a to a. Now I normalize to minus 1 to 1 because I would like to use Chebyshev polynomial in the solution procedure. Okay, next time I will come back and try to apply this Chebyshev polynomial to solve these integral equations. Okay, so I would like you to go back and study the property of the Chebyshev polynomial. If you can just simply read the thing that I have in the note here, and if you need more information, you can look at the note that I gave you in addition. Okay, I will come back to solve this problem next time. I will make sure that I will complete solving this problem in the next lecture. Okay. Do you have any question about anything here? No? Okay. So let's stop here. I will see you guys again next week. Okay. Have a good day.
Okay,ครับ